Yeah, thank you very much for this kind introduction, and yeah, always some surprising things I learn about my own life. Well, yeah, I was trying to scare some people off with this longish title, so I'm happy to have that many people here listening today. And according to the introduction, yeah, we did lots of stuff on ecosystem services very recently. However, what I would like to present today is just focusing on very few aspects of this concept, but also present some stuff that is actually also new to our group, because the global scale aspects and the global scale results that I would like to present you today are really something that we are just doing for the last, I would say, 5 years or so. And so this is really some new stuff. And actually, what I would like to do today is to tell you 3 stories. Well, in science we say 3 papers, but actually I hope that these are really 3 stories. And they have really different characteristics, and the last one is really work in progress. So there's really no paper attached to it, and this is where we really dig our heads into the data so far, and so that's it. So 3 stories for this evening, and I hope you like it. So let's start. Let's start with this really nice figure, which probably you just think about what the hell does this really mean, and this kind of really nice buildings, being really serious, and what does this has to do with science. And actually what I use these slides for just to illustrate our conceptual framework that we have, and to use it to illustrate also the conceptual framework of ecosystem services, and how this relates to land use. And so let's start again. Let's start with this guy over here, who's practicing land use. So the practitioner on the ground who's changing, who's shaping our landscapes, who's trying to trying to harvest some goods and services and trying to feed the people, and of course having some influence. Well, that's these 2 guys over there. Seem to be pretty happy. And then there's something that is frequently neglected, but probably came much more visible in this ecosystem service debate. Ecosystem functions, species, biodiversity that really supports us to obtain ecosystem services, as we see here. Clean water, food, recreational services, you name it. And there has one really important review being out in Nature by Cardinale, trying to summarize the knowledge that we have in the linkage between land use change, ecosystem function, ecosystem services, while pointing out to lots of white spots and lots of knowledge gaps that we have. Well, why do we do all this? Why came this concept up? Well, there is a guy down here who is trying to imply any kind of changes. So something should be made different, better, more efficient, whatever. And so the question is how to do it. And usually the idea comes up that this is done through money, and this is why, because money is some kind of a subsidy, incentive, whatsoever. And this is why money and ecosystem services are so closely related. And there is this paper out there from Dorf de Groot who is summarizing the big, huge, tremendous, deep data set trying to evaluate ecosystem services. But at the end of the day, it's actually work on the ground here in a really cool paper by Rebecca Goldman in PNAS, pretty old, trying to distinguish various effects of measures, of ecosystem service-based measures, or of measuring or of applying conservation sites, and trying to show which kind of concepts are much more powerful. Nice to read. At the end of the day, however, it's not about valuing ecosystem services. It's not about trying to attach any dollar values to it. But what we think or what I think in my group also, is that it's about the trade-offs. It's about how to balance out various of these services, various of aspects, indicators of biodiversity, to see what happens really with these various ecosystem services if you change in the landscape something, or if you change something in your land use intensity. And probably you most likely do something with these weird complex models and ask ourselves very frequently, why is nothing happening? Is it because these models are so complex, or is it because we're just not able to convey the story? And so, but anyhow, this is more or less the conceptual frame that we have. We're working with landscapes, trying to identify various trade-offs between ecosystem services, and yes, this is what we're doing model-based. So this would be my introduction from my side for today. And for today's presentation, I would like to focus on the upper part over there, just looking at the production of certain ecosystem goods and services and take a global view. Well, you probably know all this data here. You probably know all these figures because they are taken out of papers which are, well, at least mostly 10 years old. Human society has made a really good job in feeding the world. We were able to increase food production really by 100% within a very short time frame, within 40 years or so. And actually, increase of food production outpaced population growth. So, well, the question is, why is this actually a problem? So why are still that many people hungry? Why are that many people have no access to clean water? So we have been really quite successful. And if you further dig into that data, then you see that we did it by really, well, we must have been pretty smart because we just did it by a very, very small increase of cropland and permanent pasture by about just 10% on a global scale. But if you then further dig into it, then you see that we doubled also the area of irrigated land and we added lots of artificial substances and increased it by various numbers, by extreme numbers, fertilizers, pesticides and herbicides. So this seems to be the question that I would like to raise today is this really a success story, and what do these figures tell us, which probably you all are aware of. The other short story, which comes from Helmut Haberl, is that the human society is harvesting a quarter of the net primary production the planet is producing. No other species ever did this before, had this tremendous impact into our ecological system of the globe. Well, there are the reasons: harvesting, land use changed, etc., etc. And the question that actually comes up if you look at various papers is, what do these trends tell us, and can we continue? So there was a really, really good presentation, or a really good series of papers in National Geographic asking about how to feed 9 billion people. There have been various papers out of by Jonathan Foley and others. And of course, there was even beginning of last year the update of the planetary boundary concept. So saying, okay, there are some limits, etc. And we were trying to dig into this, and we were always skeptical, saying, okay, could we try to approach this in a somehow more quantitative way? Could we try to grasp something about possible limits in a more, well, realistic and data-driven way to answer the question, can we proceed that way, or are there any natural constraints that might pop up? And this is story one for today. And actually the story was emerged after our last big evaluation of our center, and a colleague and me were really set up with all these evaluation and strategic talking, and we started sharing bottles of wine in the evening, searching for data, and we came up with the following. We first of all made up our mind about what kind of resources do we really use. It's not only food, it's more than we use. So if you look at landscapes, if you look at the countryside, then what we use is, of course, fossil resources, and we have to open the earth for it, we have to dig it out. There are fossil resources on the globe that we use. Then, what else do we use? Land as an entity has some kind of limitation, but we would like to know how we really use it. We could irrigate it or not. Then, of course, all the commodities that we take from the field, all the animal products. And on the other hand, we use, of course, land also to obtain building material or wood for heating and anything else. And then there is also the seascape, not to forget, that we are harvesting. And well, to answer the question about how could we continue implies that we need some kind of time series data. And this is what we were collecting. Time series data of resource use over the last more or less 80, 100 years, what else was available. And then we thought about, well, if you have this time series data, and if you think about anyone who has visited a lecture on renewable resource economics knows that there is some time where if you have a renewable resource system and you're regrowing some kind of stuff, let it be fish, let it be rabbits that you're hunting, or let it be corn or crop on the field, then there is sooner or later an equilibrium where the harvest rate equals the rate of regrowth. Which is very basic renewable resource economics. And to get there, something is happening. You increase your production, you increase your amount of production every year, depending on the regrowth time, and then probably it slows down before it levels off, before you reach this plateau. And mathematic people will know it is a sigmoidal curve that emerges, and what we were looking for this inflation point, for this point where it slows down. And if you remember back to the 1970s, there was a huge debate about peak oil, saying, well, when will these resources be? Is there a peak oil year? And this was mathematically pretty similar, and well, we will have this here. So what we were doing is we were looking for the peak year of maximum production increase. This is actually what we were seeking, so the inflation point. And in doing so, these are the results. So wherever there is a question mark, we couldn't find any peak year. And wherever there is a year, it tells us that the production, the appropriation of this resource, slowed down in exactly that year. Okay, I'll talk you through. First of all, the first surprising result was there is no such thing as a peak year in fossil fuels. Surprise, surprise, because there was a high debate on peak year of oil. And these guys have been very much criticized. And then you have to dig into the literature, looking into it and see that these guys used models and made assumptions and all these kinds of things. But if you just look at the raw data, there's no such thing as a peak year. And the pressure on innovation and the pressure on changing exploration techniques still continues, so that there is still an exponential increase of producing oil, gas, or anything else. On the other hand, there's also no peak year for renewable energies, well, which is kind of nice. But if you then look back to the simple things like cropland, you see that the expansion of cropland slowed down in 1950. I'm not saying it's not continuing, but it's slowing down. And there is also the same holds true for the area of irrigated land, and the same is for applied fertilizer. And if you look at this pattern, then you see that it is 1950, 1978, and 1983. And what we as humans, as a global society, did is, from an ecological perspective, pretty clear. First of all, we chopped down forests just to plant new crops. And then, when this gets less efficient, because even the soil under these forests got less fertile, we added the nutrients that we need. Pretty nice, using the most efficient way through all these time series. Which has an implication for these 9 commodities here, which make up 45% of the nutrient intake we need as humans. We all find peak years, which then, as a conclusion, also implies or might imply peak years for animal feedstock and milk products and others. And there is a peak year also for fish caught, but not for fish farmed. So I don't know if there are further options. Okay, what does it tell us? First of all, if you just remember all these figures, and of course there are also uncertainties related to these years, then this peak year is clustered around 2006. And so what we further did was to select statistically independent time series and tested if this is really if there is a synchrony in this data set. And yes, there is. So in a chance that is less than 1 in 1,000, this is just a random pattern. So these all appeared in 2006 and around it. So this is a big fingerprint that we leave on the planet, and it's changing. And it applies some sort of limitation. So, well, why this synchrony? Well, of course, we are all using these resources in parallel and they depend on each other, and possibly producing one resource needs the other. So in terms of in terms of food production or animal production, you of course need some feedstock, etc. But on the other hand, you could also think, well, it's just happening because there was less demand, or we could substitute something. Well, let's look at these two arguments, if this is really true. Well, less demand. Well, we can show, of course, that population peaked. We reached peak child, but consumption is still increasing due to changing diets. Here with data from China and others, and also in terms of area, because the area we need for households is still increasing exponentially, especially in the Western world. So a declining in demand would require a broad-scale change in individual preferences, which so far are not visible. Only a few really have substances. Well, I mentioned that we picked out the most important commodities, crop yields, 45% of the calorie intake, and there's more slightly there's a less chance to substitute those, or we don't get anything from the moon or from the Mars, so there's nothing else to import. But even there is no it is unlikely that there is substitution between these resources. Farmed fish cannot necessarily be substituted by catched fish because there are certain preferences. There is no peak in renewable resources, but if you dig into the data and if you look at the various publications, then you see, well, renewable energies is not necessarily yet a substitution. It is just the efficiency is not there, and you have these rebound effects that if you get less energy consumptive, you do more things. And there is no consumption, no replacement for meat yet, which makes lots of people saying that we should change our diets. But I'll come to this meat thing later on anymore. Well, and then there is other critique, and this is why I was bringing up this for tomorrow's seminar with the PhD students. Then people come up and say, well, why bother? That's all. Well, we did a really great job in getting that productive. Well, we invented a mineral fertilizer, and will there be on the horizon that really keeps us having this lifestyle? The Eco-Modernist Manifesto, nice to read, very interesting, and it initiated a various debate. Well, for instance, in The Guardian, you can look at New York Times, anywhere else. So it's a very, very highly debated thing. And the major idea is, well, there will be innovation. So this is why we try to dig into the aspect of, is there a peak in innovation? You don't get this data. This is really difficult. So interesting to work together with anthropologists and others to find an answer to this. But what you can show is that there is the prices or the costs for generating innovations are increasing. So it's more and more difficult to make new inventions. If you look at the biophysical aspects, then a further increase of photosynthetic efficiency is hardly to achieve. In terms of breeding success and others, one expects 1 to 2% increase in net primary production in high performance crops, but nothing more. And finally, and this is where we have the data, we have a biological constraint. The species that we are currently live on were domesticated 2,000 years before Christ. So there is nothing essentially new coming from. So the species groups that are there, and there will be nothing substantially new. So what our saying was, and this is probably why it was also taken up, which was really making me laugh, that by Homeland Security, the paper, a peak year in these renewable resources is more frequent for the non-renewables. And a substantial growth is very much unlikely in highly productive regions where we have really limited the maximum production. And the synchrony of these peak rate years is something completely different to this debate or to this discussion that we had on peak oil, as it tells us something that we probably lack substitutions. So that was something that then brought us to the point, or to publish this and say, well, there is something more that really clearly says that there is a limit in terms of further growing. But it just gives you, let's say, a much it is just one piece of the puzzle which is actually already known, but with a different viewpoint. And I exchanged this together with Steffen, and he said, well, this is all what we are just observing, and it's more or less done. But if you're looking on the ground, if you're looking at communities that really work all day in trying to make their livelihood and generate their own food security, then the story is completely different. And this is what I would like to start with, a short summary by a really great review from Thea Czarnke on the food security issue, really trying to opening our mind to say that it is not only this FAO data which all this belongs to, but it's the smallholder farms which are the backbone of global food security, that food production is sufficient but not available to the hungry and not really correctly distributed, and that the use is inefficient, and that aspects like land grabbing on the ground really jeopardize these aspects of food production. And so what the next question would then be, if this is the global boundaries, what can we learn about what happens on the ground? But even embed this into global patterns. And this was something that we were struggling when we started this global research project that I initially mentioned, and said, well, knowing all these biophysical constraints is nice, but could we also, with this global perspective, could we understand something on what the social and what the economic system tells us on land systems, and could we learn something on global pattern with this respect? And we started this endeavor also by not pointing into any direction which we try to derive from it, but we were first of all collecting data that is characterizing land use systems on a global scale, which the first thing is very easy things like land use input outputs, cropland, trend that we have, pasture, etc., fertilizer. So more or less all the biophysical things that we know how we deal with the land use system. But then we also accompanied another thing which is also pretty obvious, like the environmental conditions, temperature, diurnal temperature range, etc., solar radiation, climate anomalies, etc., and also, where available, socio-economic conditions. Some things like gross domestic product, population density trend, even travel time to major big cities, political stability as such. So all things that might determine a little bit what is possible in this region on a global scale. We did this on raster-based analysis and just let the data speak and try to find clusters which are grouped together, spatially grouped together, and then dig into the data and try to find what is really, what kind of stories can be told by these different patterns. So there's lots of math behind and some stats and some smart people trying to analyze those, and then another group of smart people who try to visualize the whole thing, and this was the really nasty thing to do. So what you see here is a map that you probably know, and you probably grasp lots of patterns that are very, very clearly. So there is the tropics and the rainforest things, and there is the European and the US Midwest is red, and there is, so all these things, but there are stories behind. And the stories are, the story goes as follows, that we can now characterize these colored regions, which we call archetypes, by these 32 variables and their difference to the overall average. And by this, for instance, this red pattern appears, which is this intensely used agriculture, lots of energy input, high GDP. These countries do not really depend economically from their agricultural production. They have on average, pretty high biodiversity, surprisingly, so species richness in this respect, and well, pretty good political stability and provide lots of food to the world. Then there is, of course, these green colors, biodiversity-rich regions, mostly the tropics, less used, low productivity in terms of agriculture, low political stability, also well known. But 0.3% of the terrestrial Earth surface show these gray patterns, which you don't see from the distance, but these are mostly the degraded areas in the tropics, losing biodiversity due to clear cuts, losing ecological functions, etc. And the surprising thing is, well, if you know it, then it's not that surprising. I like Windows. That's great. I made it. These are the countries that are surprisingly, really highly dependent on their agricultural productivity. Their GDP is more than 20%. Their GDP consists more than 20% out of agricultural production. So these guys are not only losing their biodiversity, they are losing their ground in terms of being really productive. And then there are these brownish colored areas with a large yield gap, and all these other stories behind, but the socio-economy tells us with a very poor connection to infrastructure and with a very low, on average, very low political stability. So approaching these countries in terms of, under this umbrella of closing the yield gap might work, but not necessarily with the political and governance pictures that we have in mind coming from this red type of six-corner shape. So if you look into the paper, then you see a figure like this, which illustrates these statistics much more. You see these different categories, A, B, C, land use input, environmental conditions, and C, socio-economy. And every time where there is a plus, then this variable is 1 or 2 or 3 standard deviations above the global mean. And so you see all these stories and all these regions characterized by it. And as there are stories behind, you can then ask for what does it really mean and what can we use this as to sort out possible management options across the globe. So this was more or less this story 3, and now if we dig into it a little bit further, and now we ask the question, so if we change land use there, if we try to make any kind of recommendations, then let's go back to this nice farmer on the upper left corner and this little bee species in the middle. So what do we really know about this relationship between biodiversity and production of agriculture, so ecosystem services in terms of production? And that's actually a surprisingly difficult story. And this is something where we would then like to dig into all these colored shapes. And this is what we tried to do pretty recently and haven't finished yet, and still, it is still ongoing work, but really exciting. So to do so, we first of all started to conceptualize this. And this is why I kept this conceptualizing thing in the title. And we were actually rethinking, from an ecological point of view, rethinking how to characterize landscapes. And we thought about, well, if we're trying to get our hands on characterizing land use intensity somehow, it would be great if we could distinguish landscape composition, land use intensity, and land use configuration, which is not that difficult, but if you try to sort out and try to describe relationships based on these variables, but purely looking at land use intensity as one variable, it could drive you crazy because, well, I'll tell you. First of all, if you just try to relate landscape composition with production, then, of course, the more land I use for agriculture, the more production I gain, and there is possibly a linear relationship. Very easy. 100% maximum production. Okay, the next thing is what happens to land use intensity if you look at production? Something like this, you could agree. So the more fertilizer I put on the ground, keeping the same area under use, not increasing the area in total, but just using one spot, same area, increasing, there will be, of course, there will be something like a saturation, something like a Michaelis-Menten type of thing that really levels off because this nutrient or this substance I put into the system does not help anymore with further production. Okay, the other variable was biodiversity. What happens to biodiversity in terms of land composition? Well, this is an easy one. Well, because this is just the inverse of the species-area relationship curve, which tells that the more natural habitat I have, the more species I have, and this is a nonlinear function, and we just turned it around. That's easy. And now it becomes really complicated. For intensity impact on biodiversity, well, there might be a decay, because the more fertilizer, the more disturbances we put into it, it of course goes down. How this happens? No idea. And then the question with the land use configuration. Well, in landscape ecology, there is a really intense debate about it. Is there really a relationship, and could we really prove that there is something? So we kept it that way, assuming or just telling two stories to it. Production might increase the simpler a landscape is structured, because you can drive with larger trucks or something and be more efficient if you have something that is not depending on ecosystem function. But if you have orchards, if you need pollination services, etc., then you need some kind of structure. So it might be also the other way around, that you need some kind of fragments. And for the biodiversity effect, even so, it might be that you need large patches because of the large mammals, because of the species that have a larger species range. But it might be also that you have more fragments because you have mobile species that can adapt to it. We don't know. So, but if you put this together, then it becomes clear that it's actually not, and it's not of any use just to comparing two options, just to compare something protected against something that is in use. But it's the gradient in between that we would like to understand. It's the gradient in between that we need to understand to level out certain ecosystem services and certain ecosystem functions. It's not about just putting something at the side and don't touch it. How should we do? 80% of the global land surface are modified somehow by people. So actually, it's what we are interested in, or what my vision is to further study, is the gray shade in between. So our proposal, if you put this together, then you get two graphs which have this kind of leaf-shaped relationship between biodiversity and production, and a combined composition matrix that tells you something on the human impact on the landscape. And if you map these both together, then the relationship between biodiversity and production might look like this on the lower right. So these colored arcs of these leaf shape translate identically to these two axes. And what we really want to know is, how do we maneuver, how do we move within this gray shape? Could we, for a certain landscape, for instance, increase somehow intensity, but not losing that much biodiversity? So what is our option space? Rather than just looking at the big black points that we have there, and that was done in the recent years. So our proposal is to link spatial structure of landscapes with the biodiversity agricultural production relationship, and synthesize empirical knowledge on this question, which we now do with a meta-analysis. And what actually we try to come up is to overcome this dichotomous view and really gradually understand land use intensity. So this is, well, there are lots of studies out there. One which we are pretty proud of is one of my PhD student, Katharina Gerstner, who is also very much intensely collaborating with you guys here. And she did a meta-analysis just on the relationship of land use intensity and plant species richness, showing that there is, of course, a negative impact usually, but this has to be separated by biomes and by region, not that there are lots of variables that modify this relationship. And what you see here is the overall effect size, and if it touches zero, then there is no effect, but if it's going to the negative, then there is a negative effect, for instance, in grasslands by fertilization, but there can be also a positive effect for certain biomes. And the other pretty cool study that came out recently is this by Tim Newbold. This came out 2015 in Nature, who not only looked at species richness, which is number of species. Katharina did this for plants, but these guys also looked for abundance, which tells a completely different story, because number of species doesn't help you anyhow in terms of understanding ecological functions and resilience and stability. So these guys also looked at the abundance, showing that the abundance patterns are less likely significant, but the richness patterns are. And also Tim tried to distinguish between very low, minimum and high intensity land use systems, and showing really cool results. And actually that matters. And this is actually a look back to 2012, where we again looked at FAO data and trying to get an idea of these valuing ecosystem services, of this monetary thing. And we did, again, very simple study using all FAO data we have on pollinator-dependent crops, and from Alexander Klein's paper trying to calculate the proportion that pollination or the relevance of pollination for getting these crops, and then we just multiply this by the market price. And so you get a value of how much pollination really is important in terms of monetary value. I don't care about the value. It was something gigantic, 160-something billion US dollar. That's not the problem. What we then did also do a time series analysis and looked on what happened between these different prices of pollinator-dependent crops and of non-pollinator-dependent crops, being able to show that the prices for pollinator-dependent crops increased much quicker in the last 10 years than for the non-pollinator-dependent crops. So there's something going on. We are losing some kind of function, even in seals on a global pattern in monetary terms. And if you look at the maps, then of course you see all these hotspots of high value of pollination service. The red colors tell us there's a high monetary value, and the grayish one there's no data, and the yellowish one is low monetary value. And to see all these areas are equivalent to these red areas where there was a high intensity cropland system with lots of intensity input. So it matters. That's the point. So what we and the reason why this matters you can get from a simple map overlay, looking at where do we produce stuff and where do we have species richness. And this is something, a very simple overlay, where the reddish areas, there we have high production rates in crop production, but also high species richness. And if you do the same thing for land use change, then you see where the pressure is in these areas. Cropland change, reddish color, high species richness, and this is where the possible conflicts might occur in the next years. So, as I mentioned, we try to quantify this leaf shape over there. And what we did was we did the meta-analysis, searched for papers that try to study the relationship or how land use is modifying the relationship between agricultural production and biodiversity. Well, biodiversity, species richness again, because this is where you get the data, and all the other stuff is really sparse. And we look at agricultural production. We don't look at any kind of experimental sites that is just trying to calculate NPP or something like this. We just really look at real landscapes with real farmers with what they really want to do with something. And well, I don't recommend anybody to do these kinds of research, because if you have these broad questions and enter broad search terms into Web of Science, you get high numbers of papers, 10,000 or more, and you have to scan all those. So this was a really complicated thing, but we had some smart people in the group who then did this with some kind of data mining techniques, just using a training data set where we scanned 2,000 papers and trained it and then applied it. So, and we were able to check for the results. So at the end, we end up with about 200 papers which can be coded, which can be analyzed, and which at least give a pattern that we are happy about, because it, first of all, proves underpins our assumption. Well, what you see on the x-axis is the response ratio in yield, meaning that a 1.0 means there is no change in yield, and if you go to the right to these hardly seeable 2.72, then there is an increase in yield by a factor of something 2, and if you go to the left, you see a decrease in yield. And on the y-axis, you have the response ratio in species richness. If it is equal to 1, there's no response, there's no change in species richness. But if you go up, you have an increase in species richness, and if you go down, you have a decrease. And the red cross in the middle is our overall grand mean, telling us if you intensify, oh, I forgot something. All these points there are the effects of what happens if I intensify in the region. So what happens if I put more work, more labor, more energy, something into it, more disturbance. So the point is the effect of intensifying the land use. There we are, we made it. And the overall grand mean, which is the green cross, tells us that there is a significant effect, an increase in yield if I intensify, and a decrease in biodiversity. lots of work, and at least the first result is plausible. The others might be some more questionable, but actually we are into everything. So just to explain how we did this, we categorized land use intensity in 3 levels. And so low, medium, high. Low is more or less undisturbed, and we did this for various landscapes, such as for forests, for pasture, as well as for agriculture. And then we can study intensification within one class, meaning that I'm just doing a little bit to a very low intensity system, or I do a little bit to a very high intensity system. And we can compare what happens if we move between, if I just clear cut the forest and then put something like soybeans in there. So all these cases are captured in there. And this is what's shown in this graph, which is, as I admit, very preliminary. So what you see is, especially in these low cases, where you have really a low land use intensity, if I intensify a little bit more, then I get a huge positive increase in yield, but also a slight positive increase in biodiversity, which proves us something like the intermediate disturbance hypothesis, that there is, if I do something to the system, like our cultural landscapes evolved here too, that there's something that might happen, that there's something also not doing that bad. And all the others, kind of complicated, and what we are interested in is, could we now sort them out by these various ranges we had in this leaf shape thing. Even more preliminary is this one, because we look at various land use types. And this is what you see here is that this positive effect mainly might be on pasture land, where it is, of course, very easy to put another sheep onto it and have a higher production by not disturbing the biodiversity. So again, very preliminary. Still, we are still on coding. We just corrected the last errors in the stats. But another even more preliminary thing is we can also relate this to biophysical covariates and see that the more NPP, the more we come into the tropics, the more is this difference between the change in biodiversity and in yield, which is also kind of logical. Okay, I'm coming to an end. What I try to explain today, and I hope you had some fun with it, is that land is a limited resource, which seems to be pretty logical, but anyhow, I think there are some people who would still say that this is not a major issue, and is utilized by many people, and this is, although from an economic point of view you would say why it's not a common good, but the way land is managed these days globally feels something like it's a global good, because actually the rules are really kind of difficult to deal with it. So my major point at the very beginning was that we need a multifunctional use of these things, but the really challenging thing is to level this out and understand these trade-offs. And as you've seen here, where we first of all try to get this relationship between biodiversity and production, it's not that easy. But I think the major message is to overcome this protection, this dichotomy of protection versus use, and to get more information on the gradual changes and what happens in the areas. And actually what policymakers ask us various times is, where should I put any kind of budget, and where do I do most good and where do I do less harm for any gradual change, rather than coming up with a black or white solution. If we accept this idea that land is a common good and that we have to find an idea of how to manage it as a large global community, then we have to develop somehow the appropriate instruments to do so. And I think this is pretty difficult, because first of all, to have instruments, you need to know where to go. So what do we really want? Well, there is a CBD regulation telling that we want to have these number of protection sites, but as I mentioned today, well, it's all these other aspects in terms of how intensely do we want to use these landscapes is not clear at all. And secondly, then you need some kind of instruments to apply these. And my point is that although you probably all know these kinds of IPCC and IPBES gremia, there is no one else who's looking really consistently on land use. Land use is in all these global panels just a covariate, but not the core. And this is why I would like to ask why there is no intergovernmental panel on land management, but anyhow, I don't know. I would like to I would like to thank lots of people. The archetypes team, Tobias was involved, and some others from GLUES. So these are results from the Sustainable Land Management program that I was happy to lead the last couple of years. The biodiversity and productivity study, or we call it LUPDIS team, was a funding measure by CSync, and we had a really cool group, some people from my group, but also some people that are really into meta-analysis, like Jessica Gorevich, some people from Stanford, University College London, so it was really cool. Well, and the peak team, well, this was something like a group that was really upset with the last evaluation, had lots of wine, and grabbed this data together, but then had really stuff in either, first of all, writing the paper and responding to all the critiques that we got. I'm looking for your questions. And these three guys that started this peak paper got motivated by a presentation from Lester Brown at the last Eco Summit, and he was presenting this graph, which is the meat consumption in the US. He was really happy, saying, wow, there is a peak. Well, there's something is changing, and we have to understand why it's changing. Well, he's completely right. I don't know why US population is consuming less meat. It might be the financial crisis in 2008. I don't know. But to understand how these processes change are the really key things to change something on the ground. Whoever wants to learn something about population dynamics, I highly recommend the TED Talks by Hans Rosling on understanding why we had a peak child thing. But at the end of the day, I would like to close with this quote. Anyone who believes in indefinite growth in anything physical on a physically finite planet is either mad or an economist. Well, according to the introduction, I'm not an economist, but I dare to bring this quote because Kenneth E. Boulding was an economist. So thank you very much for your attention.